particular juncture because it's warmer here right now than it is in Texas, where I came from, by a lot, in fact. So today I'm going to talk to you a little bit about some of the work that my group does on what we consider to be different avenues towards sustainable nuclear power. Most of the work that I do in my group is on reactor design and fuel cycles, and it's really geared towards dealing with the public perception of what you might consider to be the overriding concerns about nuclear power. And in the last 5 decades, for the general public, those really haven't changed very much. People have remained concerned about the control of proliferation-sensitive technologies and materials, ostensibly things that could be used for the manufacture of nuclear weapons. They remain concerned about safe reactor operations. You want to avoid accidents like the ones at Fukushima or Chernobyl or back in the 1950s at Windscale. And people have remained concerned about the production of long-lived radioactive waste. And in my group, what we mean by this is spent nuclear fuel. Now, for the nuclear engineers in the room, you can debate whether or not these things really are concerns that you have to deal with, but from a public perspective, they are. Now, I don't know if everybody in the room is a nuclear engineer, but I'm just going to take a second to orient the conversation if you're not. This is a schematic representation of a kind of reactor that you might find in operation in the US right now. It's a boiling water nuclear reactor. And you've got the reactor vessel here, and you've got a lot of componentry on the inside, but the most important part for my group is the reactor core. Now, those cores are made up of fuel assemblies, and the fuel assemblies are made up of fuel rods. And for the vast majority of reactors operating worldwide, these fuel rods are made up of a ceramic form of uranium called uranium dioxide. Now, when the fuel goes into the reactor, it's all uranium and it's all oxygen, for the most part. And when it comes back out, though, the better part of the periodic table is represented by what's in those fuel rods. And there are literally thousands of isotopes that have built in over the time that the fuel is in the core. In very general terms, you can group them into 2 categories: fission products and transuranics. And the reason that I do that is because they behave differently when they come out of the reactor. And that's shown schematically here in this figure. So this is decay power in watts per kilogram of spent nuclear fuel, and it's time post-discharge on the horizontal axis. And the data curves that you see here correspond to the contribution from the fission products, the contribution from the transuranics, and then the sum of the 2. Now, the thing I want to draw your attention to is the fact that the fission products decay away pretty quickly. So after you've gone out 500 or 600 years, for the most part, their contribution to the decay power has largely disappeared. The reason is because they have relatively short half-lives, for the most part 50 years or less. Now, the isotopes of the transuranics, though, some of those have much longer half-lives, and as a result, they're radioactively persistent for much longer periods of time. Now, the upshot of this is that when people talk about limiting the radioactive signature of nuclear power, what they're really talking about are different ways of getting rid of the transuranics or limiting their production. Now, in the United States, what we currently run is what's called a once-through fuel cycle. You mine uranium ore, you fabricate fuel, you burn it, that's the euphemism, in a conventional reactor, and then you discharge the spent nuclear fuel to some kind of storage facility. Right now it's an interim storage facility. Ultimately it's intended to be something like Yucca Mountain. Now, the problem with this is, if you think this is a problem, is that this spent fuel contains transuranics. And so if you're just discharging it to a storage facility, those transuranics are building up someplace. And that's shown here in this figure. So here you've got mass of transuranics on the vertical axis, you've got time on the horizontal axis. 0 here corresponds to a datum year, like 2014 or 2015. And this line then represents the additional year post the datum date of transuranics that would accumulate somewhere in the United States as a result of running our current nuclear fleet. And the data were generated under the assumption that the capacity of that nuclear fleet is increasing by 1.8% per year. So there's a little bit of increase in the slope here. Now, people have debated for a long time different techniques that you could use for changing the slope of that line or perhaps capping it in some fashion. And there are only a limited number of options that you have for doing that. One would be to recycle the transuranics in things called fast reactors. These differ from the reactors that we have in operation in the US right now in that they have very high intensity neutron fields, high energy neutrons. And those high energy neutrons are very good at causing these transuranic elements to undergo fission, turning them from transuranics with long half-lives into fission products with relatively short ones. The other thing that you could do is you could recycle these transuranics using conventional reactors, the kind that are currently producing them. And finally, if you could figure out a way of limiting the use of uranium in nuclear fuel altogether, you wouldn't get any transuranics whatsoever. Turns out that uranium is the gateway to the transuranics. You have to bombard it with neutrons to even produce them. So if you could run a fission reactor without ever having uranium in the core, you wouldn't get any transuranic material. For physical reasons, it's not possible to do that, but there are ways of limiting the amount of uranium that you put into reactors, and I'll come back to that point in a little bit. Now, of these options, the one that's received by far the most attention in this country and elsewhere is fast reactor recycle. And the idea here is that you take this discharged spent fuel from the conventional fuel cycle, and instead of putting it in storage, you run it off to a reprocessing facility. And there you dissolve it in something like nitric acid, and you chemically separate out the transuranic elements and use that to manufacture fuel. And you put that fuel into one of these high energy neutron fields in fast reactor, and the idea is that it burns these transuranics out while it sits in there creating energy. You then take that spent fuel and you run it back off to the reprocessing facility. These reactors are then designed in such a fashion that every time the transuranics pass through them, you burn some percentage of that material down. So a really typical ratio would be you put a kilogram in of transuranics to get a half a kilogram of transuranics back out in the spent fuel. So you run this then in an infinite loop, and it has a really profound effect on the total trajectory of transuranics that you have to store someplace. And that's shown here. So these are the data that I previously showed you of the accumulation of transuranics that you'd expect from our current fuel cycle. Mass on the vertical axis, time on the horizontal axis, datum year. Now, if you were to couple our traditional fuel cycle to fast reactors of the kinds that I just showed you, this is what the inventory might look like over the course of 100 years. Now, there are 2 points to note here. One is that you have about an 8-fold difference in transuranic inventories between these two options 100 years out. But perhaps the more important thing to note is that this fast reactor option is tending off to an asymptotic limit. And what that means is that you could produce another 100 years worth of nuclear energy, but with a fixed inventory of transuranic material. And in a nutshell, that's why people are so interested in the development of these reactors and this kind of a fuel cycle. It offers the means for being able to produce ostensibly a very large amount of nuclear energy, but with a fixed inventory of waste. Now, there's a problem with this, and that is that people have been trying to develop commercially viable fast reactors for as long as nuclear power has been around. And at the moment, there are no vendors that are selling any kind of fast reactor that would be viable in, or commercially viable in a Western market. And it's been enough of an issue that people have begun to wonder, and certainly people in my group have, as to whether or not it wouldn't be possible to achieve similar transuranic reductions, but using the kind of conventional reactors that we have in operation right now. Now, one method that the French have looked at extensively for doing this is known as MOX Recycle. The idea here is that you discharge spent fuel, you send it to reprocessing, but using current generation reprocessing techniques, you don't pull out all of the transuranic elements, you just pull out the plutonium. And you turn that into an oxide, and you mix it with uranium dioxide to create a mixed oxide fuel, hence the name. That then goes to a conventional reactor, and it's used as fuel, and is more likely in most scenarios than discharged to come to some kind of repository or storage facility. Now, it turns out that this doesn't have a really big effect on your overall production of transuranics, and the reason for that is because it's true that you're putting recycled plutonium into these conventional reactors and burning some of it away, but you're mixing it with uranium, and by doing that, you're also breeding additional transuranic material as you put that fuel into these cores and run the cores forward. Overall, this will give you about a 10% reduction in transuranic material. It's not really that much, and the French have shown pretty convincingly that it's also more expensive than a conventional nuclear fuel cycle, so it's not a really attractive option. Now, something that you could do, and we work on this in my group, is you could use inert matrix recycle instead. Now, the idea here is that you take this spent fuel and you run it off to a reprocessing facility, but as with the fast reactor option, you pull out all of the transuranics. Instead of blending them with uranium, though, you blend them with something which is uranium-free, something that holds them so they can be put in the reactor core. That's what I mean by inert here. The idea then is that you take this uranium-free fuel, you put it into a conventional reactor, and it has two effects. One, it decreases the total amount of uranium that you have in this core, which means you're going to produce less transuranic material as that reactor runs. But because this matrix is uranium-free, it allows the neutron field in the conventional reactor to burn these elements out very efficiently. Now, the idea then is to design these reactors and these fuels so that they have a really long residence time in the conventional reactor, 2 to 3 times longer than conventional fuels would. The longer they stay in the core, the more the transuranic material gets burned out. You have to, though, design these reactors in such a way that they remain commercially viable. In other words, they have to operate at a viable power, they have to be licensable by the Nuclear Regulatory Commission. There are a whole bunch of criteria that you have to meet for something like this to actually work. And so that's where a lot of the work that we do in my group is focused. How do you pull that off? Now, people have proposed a lot of different kinds of inert matrices, but the ones that we focus on are different kinds of zirconium, zirconium-based compounds, and in particular, zirconium dioxide. Now, all of you are familiar with zirconium dioxide. It's what you make costume jewelry out of. It's rhinestone. And while it's a really good sparkly substitute for diamonds and cheap jewelry, it's also a remarkable material from the perspective of a reactor designer. It turns out that it's incredibly stable in high-intensity radiation fields. Ionizing radiation doesn't really break it down. Fast neutrons don't break it down. Thermal neutrons don't break it down. It's robust. It's also completely insoluble in water. Now, that happens to be true for uranium dioxide, but only at neutral pH. If the pH is low or it's high, the uranium dioxide will corrode on one end and dissolve on the other. Zirconium dioxide is almost completely insoluble in acids. It won't break down in hydrochloric acid, sulfuric acid. The only thing that it will break down in is hydrofluoric acid, and then only at elevated temperatures above 550 degrees centigrade. And the kinetics even then are really slow. And finally, it's tough. It's remarkably resistant to physical weather. Now, taken together, these are attractive properties for a matrix for fuel in a nuclear reactor, but they're also really attractive properties for a spent fuel form. If you take this material and put it in a repository like Yucca Mountain, anything that is contained in that zirconium dioxide is going to stay put. And it doesn't matter whether it gets wet, whether it gets old, whether it gets heated up, whether it gets broken. Stuff is simply entrained in there. It doesn't go anyplace. Now, from the perspective of an engineering material that you would use in a core, it actually behaves in many ways remarkably like uranium dioxide. It's got about the same melting point. It's got about the same coefficient of thermal expansion. It's a much tougher material when it comes to resisting fracture, and it's got about the same modulus of elasticity. The one area where it underperforms in a big way is in the thermal conductivity. And uranium dioxide is already lousy, but zirconium dioxide is 30% lousier. So this is actually a real engineering constraint that you have to worry about when you're trying to make sure that your fuels remain within allowable thermal limits in the core. So again, what we're doing in my group is we're trying to optimize these reactor designs, and I use optimize sort of cavalierly here, because we're not really optimizing anything in this broad space of reactor parameters. We're trying to design cores that achieve very large burn down of the transuranics and remain commercially viable. Now, the kinds of systems that we're looking at are modified AP1000s. And what I mean by modified here is the AP1000 is designed to run with 17 by 17 fuel assemblies, or 15 by 15, depending on the configuration. We run 8 by 8 assemblies in here. And the reason that we do that is it allows us more latitude in how you distribute the material around in the core. And that turns out to be really important in these designs. We have a thermal output that we insist on that sits between 2,900 and 3,300 megawatts thermal. That's sort of the lower bound for the AP1000 and the more realistic bound that Westinghouse would like this thing to operate at. The core composition that we look at is X% uranium dioxide and Y% inert matrix fuel. And the X and the Y are chosen under a constraint that the reactor has to be able to recycle all of its spent uranium dioxide fuel, but you're trying to maximize the residence time of the inert matrix fuel. By the time that inert matrix fuel comes out of the core, after between 7 and 10 years, depending on the design we're looking at, it's dead as a doorknob. This thing just sucks up neutrons, it produces none. And so the uranium dioxide is important to be able to compensate for the parasitic nature of that fuel. The reactor wouldn't remain critical if you didn't have a lot of that uranium in there. We assume that the uranium is enriched to 5% because that seems to be a commercial standard that most people adhere to. And we assume a refueling schedule of 12 to 18 months. And really, we try and hit 18 months, because that's what you do with commercial reactors in the United States right now.
But what sort of burnup do you get with that?
So, you're stealing my thunder.
Didn't mean to.
You get really high burnup. So, I'll give it away. So if you optimize these things, so you hit the 2,900 mark, you have a split with the X and the Y of roughly 70-30, and you stick to 18 months, we've been able to show that you can operate these reactors in a way that you burn down 86% of the transuranics. So, I mean, a really heavy reduction in transuranic inventories. So, in order to be able to do that, though, you have to make sure that the fuel remains within allowable thermal limits. Usually when people hear me say that, they assume that what I mean is you can't melt the fuel. And that's certainly true. I don't advocate melting fuel in reactors. But that's not what it means with zirconium dioxide fuels. These are polycrystalline materials that you create a solid solution of the transuranics and the zirconium dioxide. And you have these little nanoscale crystalline domains in the fuel. And they butt up against each other with sort of random orientations. When these fuels get above about 1650 Kelvin, those grain boundaries begin to move. And in fact, they begin to grow. And one of the things that happens when those things become mobile is you sweep fission gases out of the fuel and into the plenum. Now, people have done in-pile tests in Halden and Petton with zirconium dioxide-based fuels, and what they found is that when you bump the temperatures up to 2000 Kelvin, you're getting 30% fission gas release from these fuels. That's 5 times what you would expect with uranium dioxide fuels, which means that you need a plenum that is enormous on that thing, or you have to vent your fuels. So down around 1650, though, you get something which is much more similar to what you'd expect with uranium dioxide. And so we consider that to be the thermal limit in the simulations that we're doing right now. In the future, we'd like to explore vented fuels, and those can have some real advantages to them, but from an engineering perspective, they're complicated. The reactor has to maintain appropriate reactivity coefficients. And basically what I mean by this is there are 3 that you worry about for licensability in the United States. If you have a thermal transient in the fuel, the reactor power automatically has to go down without intervention. If you have a thermal transient in the coolant, same thing, power's down without intervention. And if you develop a void, you begin to boil your coolant, or for some reason some reactor material gets ejected from the core, automatically the power has to go down. So that turns out to be a pretty stiff requirement as well. And finally, this might seem really obvious, but the reactor has to remain critical in between refuelings. But again, when you try and achieve these other 2 limits and achieve high burn down of the transuranics, it becomes quite a feat to be able to pull that off. So what about these allowable thermal limits? So we deal with this in 2 different ways. So this is a top-down view of one of our simulated cores. It's a busy figure, so let me just take a second to orient you. Every single one of those squares corresponds to a fuel assembly. There's 712 of them in here. And if you've got good eyes, you can see that they all have letters. U for uranium, I for inert matrix fuel. And if you've got the eyes of a fighter pilot, you can see that there's a corresponding number. 1, 2, and 3 for the uranium. 1 is fresh fuel that just got put in. 3 is stuff that gets taken out of the next refueling. On an 18-month refueling schedule, that means that fuel is in there for 48 months. There's 7 numbers for the inert matrix fuel. 1 is fresh, 7 gets discharged. And that means that the inert matrix fuel getting removed from the core has been in there for 10.5 years. So a really long residence time. Now, what we do in these simulations is we try and position these fuel assemblies in such a way that you get a really flat power profile in the core. Nuclear Regulatory Commission likes light water reactors to have peak to average power ratios of 1.3 or less. So you shuffle these things around to get a flat power profile, but you also shuffle them around to try and minimize the temperature in the inert matrix fuels and make sure that they don't get above 1650 K. Now, the colors here then correspond to the average linear power density of the pins in these assemblies. These are simulations that we're doing with Serpent, and we tally for every one of these assemblies, and then we have axial regions in these assemblies that we tally for as well, so that you can get temperature profiles in there and encompass thermal feedback in the system. The power scale is then shown over here, and all of these colors correspond to some value over here. Now, a typical core design that just employs this kind of fuel shuffling to be able to minimize the temperature in the inert matrix fuels would give you this kind of a temperature profile. So here you get temperature in Kelvin on the vertical axis, you've got axial position on the horizontal axis, 0 is the bottom of the core, 400 is close to the top of the core. And what you can see here is you get a nice rise in temperature up to, unfortunately, about 2000 K, then it falls back down again. Too hot. All right, and no amount of shuffling of the fuel through the core that we've been able to strike on will get a temperature profile down to 1650 Kelvin or below. So the way that we get around this is we either dope the fuel itself with burnable absorbers, or we introduce guide tubes into the fuel assemblies. So this is a blowout of one of these fuel assemblies. Every one of these red dots corresponds to a fuel pin, and then these other colored dots here, greenish yellow, correspond to guide tubes into which you could insert a fuel pin, or you could observe some kind of neutron absorbing material. And in our simulations, that's boron carbide that we stick in there. And then we vary the concentration of the boron axially to flatten out or to lower the temperature profiles. And it can have a significant effect, on these temperatures. So here again is temperature in Kelvin, axial position on the horizontal axis, without these boron carbide rods in the fresh inert matrix fuel, and then with the boron carbide rods in this inert matrix fuel. And these data correspond to the hottest pins, sitting in the core. So something that we do to improve the neutron economy, though, is we pull those pins out as the inert matrix fuel ages. So after it's been in there for 18 months, it gets reshuffled, we pull out one of the rods. After another 18 months, we reshuffle the core, we pull out two of the rods. And at the next refueling, we pull out the last of the rods. And this allows the neutron economy to improve, so you get additional burn down of those transuranics in the system, and you also ensure that all the fuel pins are remaining within the temperature range that we want to see. Let me just say, this is a complicated shuffling scheme, right? You got 712 assemblies in there, and then you got 4 things on each side, inside of each one of them, that you're successively withdrawing every time you refuel the reactor. This is not a reactor supervisor's dream in terms of core structure, but it gets us to where we want to go with this. What about the reactivity coefficients here?
Two questions, if I may.
Yeah.
Can you show the map, the core map? Yeah. So if I read it correctly, it appears that there is a very large spread of linear heat rates between the central fuel assemblies and some peripheral fuel assemblies. And if you are having the same overall number of fuel assemblies or fuel pins, or core volume, say, as the AP100, 1000, I would think that the peak linear heat rate in your core is much, much higher than in the AP100, 1000.
So say that again.
So the peak linear heat rate in your core, I would guess, is much higher than in the AP1000.
It's similar in terms of, well, let me say that the highest linear peak rates that we see in the cores, they get up to about 38 kilowatts per meter. And I think that's similar to what you find in a conventional AP1000. Yeah.
And do you have, where do you include the control rods?
So we've left them out here. We assume in these simulations that you've got some kind of burnable absorber boron, which is in the core, that creates sort of a uniform depression in the system. But we would, legitimately thread them through some of these assemblies where you don't actually have burnable carbide rods in them. So reactivity coefficients. We have a thermal feedback model that we use in conjunction with this, and so we've done perturbation studies using the Monte Carlo simulations, simply raising and lowering the temperature in the individual regions of the core to see what the reactivity looks like. And I'll show you some example data from what these simulations show. So this is a graph of the thermal reactivity of the fuel as a function of the kind of fuel that you happen to be looking at. And these are core average results. So this bar here represents the average behavior of all of the fresh uranium dioxide that's in the core after you start it up after refueling. And IMF 7 here corresponds to the inert matrix fuel that you're just about to take out after you shut down at the next refueling. The important thing to note here is that on a core average, all of these fuel forms have negative coefficients of thermal reactivity, which is exactly what you'd like to see. Now, we've done similar studies for the moderator, and here it matters a great deal, where you happen to be. Are you at startup or are you at shutdown of these cores? Because you have different isotopic composition of the fuel, and it gives you slightly different behavior. So here we have core average temperature, and the real behavior of the reactor is over on this end. The inlet temperature of the coolant is at 550 Kelvin, and the outlet temperature is a little bit below 600 Kelvin in these simulations. And the important thing to note is that both at the beginning of life and at the end of life, so at startup right after refueling and at shutdown, you have negative reactivity coefficients in this core. And you find the exact same thing for the void coefficient in the core. Now, I should say that these are core average results. And so if you were to take a look at the response in individual fuel assemblies in the core, this might not hold. There are, particularly the late stage inert matrix fuels in the core, they have positive coefficients, positive moderator thermal coefficients. But the average over the entire core is negative, and that's the requirement that the NRC wants you to meet. So what about the reactor remaining critical? Well, in all of our studies, it's a design criteria, so it does in fact remain critical in between. A typical K effective graph is a function of cycle time. 0 is startup, 540 is when you shut down, would look like this. So you start off with a rapid drop due to the buildup of xenon in the fuel. And then when you're building in and burning out the xenon at a uniform rate, you get a linear change in reactivity until you shut down to refuel. Now, we've also done some studies to kind of illustrate, where this reactivity is coming from. And in particular, how much of it is coming from the inert matrix fuel and how much of it is coming from the uranium dioxide fuel. And so we've done some other simulations. These were generated not with Monte Carlo codes, but with collision probability codes that we developed in-house. And it's easier for us to break out the contribution from the individual fuel forms with this. So again, here you've got K effective on the vertical axis, you've got time on the horizontal axis. We start at 5 days in here, which is why you don't see the xenon drop right here. But the important thing to note is that this is the collective K effective of the reactor. This is the contribution which is coming from the inert matrix fuel. By the time you hit 300 days, your inert matrix fuel collectively in the core is already a net neutron sink. So you've got to make it from 300 days to 540 days with something else driving the reactor. And that something else is the uranium dioxide in the core. So this is what determines that XY split in the composition of the core. It's always a constraint that we have to operate with. So, I've already answered this question, but what can you achieve with one of these things? So if you're willing to operate at 2,900 megawatts thermal, take a 10% hit in power, and have a split of the core, 72% UOX, 28% inert matrix fuel, and adhere to this 5% enrichment requirement that people generally adhere to, and stick to an 18-month refueling schedule, you can get an 86% burn down in the Transuranics. That's big. And you can see that in this graph. So here are these data that I showed you before. Transuranic mass on the vertical axis, time on the horizontal axis. Standard fuel cycle, that's what you would expect. One of these fast cycles, that's what you'd expect. And the inert matrix fuel cycle sits right next to what you'd expect with a fast reactor option. Little bit more transuranic mass at the end of 100 years, but it does pretty darn well. And importantly, you can implement it using conventional kinds of reactor technologies. You don't have to wait for fast reactors to become commercially viable. So from this perspective, it's attractive. And we in my group really consider this to be a bridging technology. Ultimately, you'd like to get to fast reactors. But this is a way to be able to kind of counter the arguments that have come out of MIT in recent years that you shouldn't pursue reprocessing-based fuel cycles because the reactors to implement them don't exist. Well, they do. So what can we conclude, from what we've done so far? Conventional pressurized water reactors can recycle their own transuranics, and they can achieve a really high degree of transuranic burn down. The inert matrix fuels, despite the fact that they have low coefficients of thermal conductivity, can be kept within reasonable limits temperature-wise, and the reactivity coefficients can be kept within a licensable range. So the U.S. Nuclear Regulatory Commission might actually consider looking at a core like this as being a viable form of recycle strategy. Now, I will say that there is a problem with this, and that is that it relies on a kind of reprocessing that can very efficiently separate transuranics from fission products. And in particular, you have to be able to very efficiently separate all of the transuranics from the lanthanide fission products with which they're entrained in spent fuel. That kind of reprocessing technology doesn't exist on the industrial scale. And a lot of people will tell you that it's a roadblock not only for inert matrix fuel cycles, but also for conventional fast reactor cycles, like the one that I previously showed you. A lot of people think that the more difficult thing to do is not to develop the fast reactors, but to develop the kind of reprocessing that you would need to make them work. It's a tough problem. People have been working on this for 5 decades. It's an open question is how do you do this efficiently, cost effectively, and on an industrial scale. So this has prompted us to look at other kinds of reactor technologies that might be able to achieve low transuranic production, but that would work with conventional reprocessing technologies. And unfortunately, the one that most people envision for doing this is also a kind of fast reactor. In our work, it's a kind of breed-burn reactor. Some people might disagree with the term breed-burn here, but it's a breeder reactor. So
before we move on, may I ask a question?
Yeah.
About the AP1000.
Mm-hmm.
So the power level of the inert matrix fuel assembly will vary significantly over its life.
That's right.
And how do you manage the change in the power per assembly?
So I could have showed you a little movie that shows the time evolution in between refuelings of one of these cores. And basically what happens is the colors don't remain fixed in the diagram, they shimmer. And they shimmer because there's a different evolution of the fuels at every single location within the core. And so in the simulations that we're doing, we don't have enough. We have a lot of computational power down in Texas, but we don't have enough to be able to determine all of the properties of the reactor at every single time point in the simulations. So typically what we're doing is we take a look at the behavior of the fresh fuels, and we take a look at the behavior of the old fuels. And we assume that if you can meet the criteria between those two endpoints, or at those two endpoints, that everything in between will behave the way that it should. It's an idealization, but it's an assumption that we're currently operating. Usually when I give this talk, I say that people may very well have heard of breed-burn reactors if for no other reason than because of the involvement of Bill Gates in a company that's looking at ways of developing them. At Berkeley, it might be because David Greenspan is here, and because of his involvement in the development of the analyses of these kinds of systems. To understand why somebody like Gates or why people in general might be interested in this kind of a reactor system, it's always useful to take a step back and ask what an ideal nuclear reactor might look like if you could wish it into existence. And just say that you'd want these things to be self-stabilizing. You'd want them to be passively safe, and you'd want them to make very efficient use of natural uranium. Conventional reactors use about 1% of the atoms that are mined out of the ground. That's an inefficient use of the uranium resource. You'd want these things to produce few, if any, transuranics, and you'd want them to be able to achieve all of these things with no need for enrichment and no need for reprocessing. Now, for purely physical reasons, there's no way that you can achieve all the things in this list. But breed-burn reactors, if you were able to get them to work, would actually do a fair job of, at least addressing, many of these issues. And that's why people have been so interested in them. Let me say that conceptually, they're really easy to understand. So imagine that you had a cylinder of depleted uranium, and you were to light this thing on one end with a fast neutron field. Now, what would happen in the process of doing that is some of those fast neutrons would be absorbed by the uranium, and you get a transmutation reaction that produces transuranic elements, plutonium and other ones. And all of those transuranics will undergo fission when they interact with high-energy neutrons. So if the concentration built up to a sufficient degree, you could imagine that you'd get a self-propagating fission reaction that would move up through one of these cylinders of fissile material, breeding fuel for itself as it went, and leaving in its trail nothing but fission products and maybe a little bit of transuranic residual waste. Now, the problem that people have run into, or one of the problems that people have run into with this kind of reactor system, is extreme radiation damage to the materials in the core. Even if you could get these things to work, it turns out that the intensity of the neutron fields that are required to do that subject the materials to just inordinate levels of neutron interactions, and the materials degrade over time. And this is really the limiting issue. And it's driven by the presence of the high-energy neutrons in these fast reactor cores. Basically what happens is these high-energy neutrons collide with structural materials and with fuel atoms, and they literally knock them out of their equilibrium lattice locations. And for the most part, they relax back to where they came from right away. But over time, if you nail them enough, they will move into a different location, and you change the morphological structure of the materials, and that changes their material properties. And it's just one of those things that the material properties never seem to get better. They just seem to get worse. The problem is particularly acute in the cladding material that surrounds fuel. This is that little sheet that separates the fuel from the coolant that moves up through the core. And right now, the best materials that you have for use in these systems have only been demonstrated to maintain their properties to 200 dPa. And dPa here stands for displacements per atom. So, and these are HT9 steels. These are, I think, martenitic, austenitic steels. And they're good to about 200 dPa. That's been shown by bringing samples out of the EBR2 and out of the FFTR. So, unfortunately, a lot of work on breed-burn systems has shown that you actually would have materials getting to many, many times this dPa value. And so you either need a way of reducing the radiation damage in the core through smart design, or you need a different generation of materials altogether to use in these systems. So when I became interested in this problem, I was interested in just doing some very simple scoping calculations to understand the evolution of dPa in materials in these kinds of breed-burn systems. And what I started doing was just doing very simple diffusion simulations of a very large reactor, 20 meters long, 3.5 meters in diameter, comprised of uranium metal fuel with a liquid sodium coolant. And the two sat in a 50-50 volume ratio, and then you had some structural components in the reactor as well that were made out of HT9 steels. And I started by writing some simple diffusion codes to understand the dynamics of these waves. And originally, we were tracking a whole host of isotopes, uranium, neptunium, americium, and curium, a lumped fission product that handled the behavior of a whole range of fission product isotopes. And then we were also able to define DPA cross-sections that would let us understand damage levels in the core. So in a typical simulation, we would have this cylinder of depleted uranium cooled with liquid sodium, and we would subject it at one end to one of these really intense boundary fluxes, fast neutrons. And then we would watch the co-evolution of the materials. This little movie cycles around a few times. So here you've got flux and normalized units here, you've got position axially down here, and what you're seeing here is the co-evolution of this boundary flux and the materials up to a point where you get a sufficiently high concentration of transuranics that you get a self-propagating wave that moves down through the system at a constant velocity. Now, there are actually two waves that I'm showing here. In blue, there's the neutron field, and then in red right before it is a Neptunian wave, also on a normalized scale. And the Neptunian is important because it's the gateway to plutonium, and plutonium is what's really driving the propagation of this fission wave. And so these two things move in lockstep. People that study reaction diffusion phenomena and nonlinear dynamicists call this a push-pull wave. These two things are coupled to one another. But one of the things that we were able to get out of these simulations is also an understanding of how the DPA values and the structural components and the cladding varied as a function of position along the wave. And some of those data are shown here. So here you've got DPA, displacements per atom on the vertical axis, and relative position on the horizontal axis. Way over on the right-hand side, you're way out ahead of the wave peak. And way back here, you're behind the wave peak. It's already passed and you're ostensibly in the spent fuel. This white bar here corresponds to the location of the wave peak. And the important thing to note here is that by the time this wave hits the peak, you're already pushing 600 dPa. So 3 times the level to which HT9 steels have been demonstrated to maintain their properties. And by the time the wave has completely passed, you're pushing 1400 dPa. So when we first saw this, our reaction was, there's no way you're ever going to be able to build a reactor like this, no matter how much Bill Gates says you can. It's just not going to happen. Even if you could reclad the fuel, the structural materials in the core would disintegrate over time. But it occurred to us that the driver of this damage are really these high energy neutrons. And as a reactor physicist, I have control over what the spectrum in my core looks like. I can dope my core with light elements like hydrogen or beryllium or oxygen, and what they're going to do is they're going to downscatter some of those high energy neutrons, soften the neutron spectrum. And so we started playing around with different kinds of fuel compositions that would produce a softer spectrum in the core. And some of those data are shown here. So here you got flux in these reactors in arbitrary units, and you've got the energy of the neutron field on the horizontal axis, and 2 different spectra are shown here. So in yellow, you've got the spectrum from a sodium-cooled, metal-fueled fast reactor with some structural steel in it. And in green, what you get is if you dope that uranium metal fuel with 20 atom% beryllium. So a really high concentration of beryllium in the system. And what you see is that you do, in fact, downscatter some of these high energy neutrons and you create more low energy neutrons. Now, it doesn't look like a lot, right? You look over here and it's like, well, yeah, sure, the lines don't lay on top of each other, but they're not separated by very much either. But let me point out that you're on a log scale here, so the differences are a little bit deceptive. But it turns out that even a small change in the intensity of the neutron field up here has a disproportionate effect on DPA levels in the fuel, or at least in steels. And the reason for that can be understood by taking a look at the DPA cross-section for iron. So here you've got DPA cross-section in barns on the vertical axis. You've got the energy of the neutrons on the horizontal axis. And the thing to note here, aside from all the quantum mechanical detail, is that you basically increase considerably at high energy with these neutrons. So even if you get rid of a small percentage of the neutrons up here, it has a significant effect on total DPA levels. Now let me say, with this kind of fission wave that I've been showing you, neutron economy is really tight. You produce as many neutrons as you need to propagate the wave. A few more and the thing grows in power, a few less and it dies out. So when you soften the neutron spectrum in one of these reactors, shifting up to the green spectrum, you get a lot of parasitic neutron absorption in the uranium resonances in the fuel. and that will kill the reactor. So you have to compensate for that by adding fissile material to the core, either uranium-235 or plutonium that you've recycled with conventional reprocessing techniques. And so when you create this kind of hybrid fuel, this is the effect that you get on DPA. So here you get displacements per atom on the vertical axis, relative position on the horizontal axis. These are the data that corresponded to that metal-fueled, sodium-cooled fast reactor. And here is the corresponding DPA curve that corresponds to fuel, which has been doped with 20 atom% beryllium and 8 atom% recycled plutonium in the system. And the kind of plutonium that you would get out of a conventional light water reactor whose fuel would be burned to 45 megawatt days per kilogram of initial heavy metal. Now, what you can see is that there's about a threefold difference in total DPA values between those two. Now, let me say that it's not all because of the softening of the spectrum. For these data, only about 1/3 of it is due to the softer neutron field. The other 2/3 comes from the fact that by adding that fissile material to the fuel, you actually accelerate the wave. It moves more quickly. And so it simply passes through every region of the reactor faster, and the materials are then subjected to less neutron affluence. That's 2/3 of the effect.
What is your Z?
What is my Z? What is
In meters. Is it
Oh,
in meters?
yeah, this is in meters, yeah.
Okay.
Z in meters. So these waves in these particular data, they're about 4 meters from tip to tail. So for a lot of reasons, I think that wave reactors are probably impractical. But we wanted to take these ideas of spectral softening and fluence reduction and use them in conjunction with more typical fast reactor designs. And one of the things that we've also found in the simulations that we did on fission wave is that you are far better off if you have a flat power profile than one of these super peaky power profiles that you get in these fission waves. And the reason for that is if you were to even use a fission wave reactor, the kind that Bill Gates had originally talked about, chances are you wouldn't create a reactor which is 20 meters long. I mean, that's an engineering nightmare. What you would do is you would create a conventional sized reactor, and instead of having the wave move through it, you'd push fuel through it so that you had a standing wave sitting in that core. Now, by having a really high power peak, what that means is that you hit that maximum 200 DPA level at one point in the reactor long before you hit it at some other point in the reactor. And it simply makes for an inefficient use of the reactor volume. So the reactors that we've been looking at are much more conventional in their structure. In fact, we borrowed this image from the TerraPower website because they're now looking at reactors which are much more conventional as well. And what you see here is the core, containment vessel, and then this schematic representation of cooling systems that would be used in conjunction with it. And what we've been trying to do is design reactor cores that would have very, very long core life and operate at very high power output. By high power output, I mean 3 gigawatts or right around there. For protracted periods of time without the need for any kind of fuel reshuffling or for any kind of fuel or for any kind of refueling before they ever hit a 200 DPA level anywhere within the cores. Now, one of the designs that we've been looking at recently looks like this, and this is a top-down view. If you were to pop the top off of one of these containment, one of these reactor vessels and look down, you've got hexagonal assemblies in here, and there are 2 different kinds that we're looking at. So in gray are assemblies which contain boron oxide fuel elements, or boron oxide pins in them. And these things act both to downscatter neutrons in the reactor, but also as a reflector to keep them from leaking out the side of the reactor. And those are both around the periphery of the reactor where they reduce leakage, but also in the interior region of the reactor where their presence is to backscatter neutrons out into this annular region and reduce power peaking in the center of the core. In green is the fuel. And here we're using not metal fuel doped with beryllium, but we're using uranium dioxide fuel. It's actually MOX fuel. It contains both plutonium and uranium. And this black region here is a region of steel fuel pins that sits in the core. And in the parlance of reactor physics, it's referred to as a diluent. It simply dilutes the concentration of uranium fuel in the core and keeps power peaking from happening in this annular region. Now in 3D, these cores look like this. So here you've got this outer beryllium reflector. Here you've got the inner beryllium reflector. Here you've got this steel diluent. And then in the region in between there and here, you've got this mixed oxide fuel. Now, the reason that we have these reflectors in there is to help achieve a flat power profile. And that's true for the steel region in the core as well. Another thing that we do, though, is we dope the fuel with plutonium. And we actually have a rating scheme here. And so this is a heat map of this. Blue corresponds to a low concentration. Well, if 12 atom percent is low, low concentration relative to the outer regions that rise to 16% on the outer periphery of the core and 15.4% on the top and the bottom of the core. And the idea then is that this distribution of plutonium is entirely so that you get a flat power profile within this system. We've then run full core simulations of this using a Serpent 2.1 point, whatever the newest one is. And what we've been able to find is that you can run this core for almost 15 years before you have to shut it down, not because it's run out of fuel, but because you've hit a maximum of 200 dPa at some point within the core. And you can do that without reshuffling the fuel and without adding additional fuel to the core. Now, at the end of that 15-year time frame, this is what the uranium burnup on the inside of the core looks like. So here you got uranium burnup fraction. It's the fraction of the initial uranium in the core gets burned out on the vertical axis, and then radial position and axial position here. And the heat map then corresponds to the degree of burnup. At its maximum point, it's a little bit above 20%. On a core average, it's just a little bit below 15%. So remember I said that for conventional reactors, they use about 1% of the uranium atoms? This on average uses almost 15% of the uranium atoms, so 15 times higher. Conventional reactor has to be refueled every 18 months. This thing runs for 15 years. This hole in the data that you see right there, that's the location of those steel pins on the inside of the core, so you simply don't have anything burning up there. Now, the corresponding dPa profile in here looks like this. So here you get displacements per atom on the vertical axis, radial and axial position on the horizontal axis. And what you can see is that you hit, it's a little hard to see because of the scale, but the peak dPa value at the end of life for this system is 201 dPa. So right at that edge where HT9 steel has been demonstrated to. And the hole, again, corresponds to the presence of that steel on the inside of the reactor. So really, nice performance. And importantly, you can implement this using conventional reprocessing technologies, because the only thing that we put into this fuel is plutonium, and PureX will get you the plutonium that you need from conventional light water reactor fuel. So what can we conclude from this work? Well, you can design a breeder core that can run for 15 years at about 3 gigawatt thermal output. It's actually 2.98. Before anything in that core will reach 200 dPa. You can get a significant overall reduction in transuranic production per unit of energy generated. So you get about an order of magnitude less plutonium production per unit of energy generated than you would with a conventional light water reactor. You get about the same production of minor actinides, so curium, neptunium, and americium. It's really hard to avoid, and the reason for that is because we have so much plutonium in the core at the beginning of life, and plutonium is the gateway to those higher actinides. So the fact that you got 15 weight percent, plutonium in there, just means you're going to produce minor actinides, and there's no way to get around that. And importantly, this can be implemented with conventional reprocessing technologies. So a nice property of this reactor is it has a negative Doppler coefficient. So that's really nice. So if the fuel heats up, the reactivity automatically goes down. But as with a lot of fast reactors, it has a positive Voigt coefficient and it has a positive coefficient of reactivity for the coolant in the system. But that's not unlike other designs that are out there. So finally, I'd like to thank two of my postdocs, Dr. Jeff Rechnewald. He did the majority of the simulations for the inert matrix fuel data that you've seen today, and also Dr. Andy Osborne, who did the majority of the work on the burn systems. I'd like to thank the U.S. Nuclear Regulatory Commission for a junior faculty grant that allowed me to fund Andy, and for the U.S. Department of Energy for an NEUP that allowed me to fund Jeff. And with that, I'll open the floor to questions. Yes.
Does this discussion of the breeder reactor mean that you've abandoned the conventional light water reactors that you talked about?
No, so unfortunately I left you with a reactor that requires reprocessing that doesn't exist, and another reactor another option that requires a reactor that doesn't exist. No, what we're trying to do now is come up with designs for the light water reactors that can actually recycle all of the transuranics using conventional reprocessing techniques. And what we do there is in PureX reprocessing, you develop 3 material streams. plutonium, uranium, and then this mixture of fission products and minor actinides. And conventional reprocessing can't separate the lanthanides from the minor actinides very well, but it can get rid of all of the other fission products. And so we're now looking at fuel forms that will create solid solutions with those minor actinides by themselves, and we use that as blanket material around the core. So we put inert matrix fuel with uranium back into the core, and then blanket regions that have these minor actinides in them. And what we're able to show is you can actually get a reasonably good burn down of those minor actinides if you're willing to power the reactor down. So you can't run it at 3 gigawatts. You have to dump the power down to 2 gigawatts to be able to do that. But you can get, you know, a 3-fold reduction in minor actinide inventories using that.
Does the conventional light water cooled reactor still run with 1650 as the maximum fuel temperature?
So that's a constraint that we have in there.
Well, if you're up to that temperature, then your cladding temperature is going to be much higher than it is in conventional reactors.
Oh, so
now.
one of the things that we have an additional constraint in this is that your cladding temperatures have to remain, you know, within allowable limits as well. And for the coolant velocities that we're using in these reactors, the cladding temperature hasn't been an issue for us to date. Let me say in that, though, that we're using thermal resistor models to model thermal effects in these reactors, both in the fast reactors and in the light water reactors. And ideally, you'd like to have something a little bit more sophisticated than that because...
You mean calculating temperature distribution?
Yeah, calculating temperature distributions in these systems. But the cladding temperatures don't appear to have been a limiting issue for us, you know, to date. One thing I will say is that, you know, one of the things we'd like to explore in the future is venting the inert matrix fuels. Actually run them hot, you know, so that the fission gases come off. That xenon drop that you saw in some of the data, that's because of the buildup of xenon in these things. If you can vent the xenon off, you have a lot more excess reactivity in the cores, and it becomes a whole lot easier to hit the design metrics that we're looking at. You know, so most of my interests are really on the light water reactor side because I think there's a clearer path with current generation technologies to implementing those fuel cycles than there are to the development of fast reactors. I like fast reactors. They're technologically very interesting, but we've built 17 of them worldwide, you know, in the last 5 decades. 4 of them have melted down and 3 of them have caught fire. You know, so that's not a ringing endorsement in terms of safety. Yeah.
Technical question, if I may. So in my mind, I have rules of thumb for neutrons slowing down and scattering. And basically, above 100 kiloelectron volts, it's inelastic scattering, and below that, it's elastic scattering. And so could you explain how then, if you're doping the fuel with the beryllium, which is the light element, which is supposed to do the elastic scattering part of it, how that is really getting you the downshift in energy when it's not going to really take effect until after you've already slowed down with the inelastic scattering with other elements.
Right, so I mean, keep in mind, you've got a lot of beryllium which is sitting in that core. And when we compute DPA cross-sections, we use a code called NJOY. And it takes into consideration the entire range of possible nuclear reactions that you have that contribute to the DPA cross-sections. At elevated temperatures, these are all effects which are due to particle production, so NP reactions, N reaction, N2N, N3N reactions. Those are the dominant factor, it seems, that actually wind up contributing to the downscattering of energies up at the 500 keV and above range. And I say that because I don't know if you've ever used NJOY, but it's a tough code with an 800-page manual that doesn't have an index. So when you're trying to figure out what this code does, you have to reverse engineer it. And so what we did is we built a DPA model, and then we started adding reactions to it. And as we did that, we were able to predict the behavior of the NJOY cross-sections at low energy, and then higher energy, and higher energy. And when we got to about 500 keV, it was all of these particle production reactions that were the difference between our model and theirs. And so up to the upper range, it doesn't just seem to be inelastic scattering, it seems to be the N2N, N3N reactions, NP reactions have really become important. And I don't have a good physical intuition for saying whether or not that's correct. I will just say that that's what gets you to, for our model to be able to line up with theirs.
Okay, thank you.
I would like to add that one can achieve similar performance, maybe not as good as the one that Mark showed us, without using beryllium. And we know that TerraPower recently came up with designs in which it was metallic fuel, not oxide fuel. But with enriched uranium, not depleted uranium, that will not exceed 400 dPa, or if they want to go down to 200 dPa, they will use somewhat higher enrichment and achieve the same constraint. So the function of the beryllium is not crucial.
So
maybe helpful to some extent, and may not be economically justified, but...
So actually, our conclusions are you would not want to run that fuel. I mean, 20 atom% beryllium in uranium metal fuel, I don't know if that's even possible, right? You have to talk to a metallurgist to see. We just look at it from a physics point of view. If you threw this much material in there, what would the behavior of the reactor be? Once we had established that it would have an effect, we transitioned to oxide fuels because we know that those things will perform in a reactor environment. And it turns out that they give you almost the same effect. And you don't have to worry about the mechanical properties, of the material when you introduce a whole lot of atoms of something light in there.
An oxide fuel with is a fast reactor or a thermal reactor?
So we use them in both. So the oxide fuels are in the light water reactors, but they're also in the final simulations that I showed you of that core structure, that all uses oxide fuel. And there are benefits and minuses to that. So I mean, for example, melt refining, I don't think would work with an oxide fuel. But conventional reprocessing like Purex, that's what oxide fuels work well with. Yeah.
So for the TRU, zirconium dioxide fuel, dioxide matrix, do you have any irradiation experiment for this kind of fuel? Why you decide to load about 50% TRU in the matrix?
So it's a stability issue. So Transuranics, particularly americium, when you load these materials into a fuel, they create phases in the fuel. So you've got the zirconium phase, you've got the plutonium phase, you've got the americium phase. And you want the phases really to sort of be uniformly distributed. People have found experimentally that when you bump up the transuranic content much beyond 15%, you start to get phase stratification in these fields. And so the americium will begin to pool with other americium atoms. And that causes discontinuities in the fuel that would likely lead to failure. And so at 15%, it's kind of on the upper bound of dilute for avoiding.
So there are some experiments for this?
Most of the work on that has been done at the Paul Scherrer Institute. And most of in fact, all of the impile work that I'm familiar with was done by people at Paul Scherrer and Paul and we used to have a program for this in the United States, but as with many things nuclear-related, it kind of faded away.
Because we are also very interested about these TRU topics.
That's right.
We want to know as much as possible.
So there are some people, now at Stanford, a guy named Rod Ewing, he used to be at the University of Michigan, now he's gone to Stanford. He takes a look at a different kind of zirconium matrix. It's called a pyrochlore. And those pyrochlores, for reasons that aren't clear to me, don't encounter this phase stratification problem until you're up above 40% transuranic loading. So they seem to be more stable from a thermodynamic perspective. Yeah.
So a lot of the stuff you were presenting was really interesting, and I was particularly fascinated by your breed and burn, or the reactor that would operate for 15 years without achieving a high enough dose to the materials such that they would be structurally compromised based on what we have. Theoretically speaking, what would one do after 15 years of operation when some structural material in the reactor had achieved 200 dPa? Would you swap things out? Would you?
Yeah, so I think that this plutonium profile in the core would require that you replace the core all at once. But this is a complicated distribution of material on the inside of the core. It's sort of a manufacturing nightmare. And you definitely wouldn't want to core shuffle this thing. This is a package plant. And what we'd really like to do is we'd actually like to reduce its size a little bit. So you get it down below 3.5 meters, you can put this thing on a flatbed or a rail car. And then we would envision this just being something that you bring to a reactor site, you uncouple the old one, you stick in the new one, and then you send this thing back off to a Purex reprocessing facility. Yeah.
Okay, that's one.
How is the NRC up to speed on some of these new ideas? So like when you present them, these things, are they able to analyze them, or are they pretty set on what's going on now?
Well, so one way to answer that is to say that the NRC has a suite of codes they use for licensability, and they are entirely geared towards light water reactors. So their ability to license a fast reactor for commercial operation, I don't think that it exists. That said, they've got a lot of really good reactor theorists and engineers that work with the NRC, either at universities or at the NRC per se. So just the fact that they don't have the capability right now doesn't mean that they couldn't put it in place.
So they have many consultants. Again, I'm not familiar with the way they work, but they have many consultants that they could bring in if you presented this to them.
So one of the former NRC directors, Dale Klein, is on the faculty down at UT. And so when Dale has questions, he'll come to us. We're 4 people, so there's not much of us to come to. But he'll also go out to other people and ask questions. So I think that maybe to get at the core of your question, if there were a serious desire to develop fast reactor technologies in the United States, I don't think the NRC would be the limiting factor.
Okay, let us thank again.